So my name's Joe Taylor. I'm a haematology consultant at the Royal London Hospital, and I'm working with Daniel Kreuter and Zhang. So we're an international consortium, and we're focused on the development of machine learning models in order to improve diagnosis and management of disorders that you can detect signatures for in the full blood count. And we're working across a range of different conditions. And as you can see, we are international. We have sites in the UK, in Europe, in the Gambia, in Ghana, in India, in Singapore, and in Japan. And so far we have 3 of those sites, hopefully. Sorry, I'm having a bit of trouble with this slide. I'm not moving on. Take my word for it. So 3 of these sites, or rather 3 of these countries, and we now have connected internationally for Federated Learning. Sorry. Okay. And we're doing this through our partnership with Flower, who've helped us to integrate securely and pretty seamlessly actually into our healthcare infrastructures and also accelerate our deployment of FL models. I'm just going to talk very briefly. I know it's been touched upon in other talks as to why FL is so important, particularly for healthcare. And one of the reasons is ethical. There's been a slightly unfortunate history of extractive research where institutions from richer countries move into poorer countries and ask for their data, and then they lose control over that data and don't necessarily see the benefits from that research translate back to their own patient sets. And so one of the advantages of FL is that the individual institutions in our network retain the ownership over their data and control of how it's used. And closely related to that is data privacy, because as a result of this, we've seen very different and quite strict rules regarding the transfer of data for healthcare research out of different nations, and so FL allows us to stay within the legal restrictions. We've touched upon already the large data scale in healthcare, so the physical barriers to transferring massive amounts of data between institutions is a challenge. I think another talk has mentioned how we're dealing with often rare conditions, and these rare conditions are siloed amongst different sites, and so it's difficult to train models that can capture rare diseases. And finally, real medicine is not IID. So we see significant differences in disease prevalence in different institutions. We see difference between local populations, and actually something that we've noticed a lot and had to learn how to deal with is even down to the differences in lab calibrations between different analyzers in different sites. We see very marked variations in data. I'm going to hand over to Daniel, who's going to tell us a bit more about a specific case example.
All right, thanks very much, Joe. So hey everyone, I'm Daniel. I'm a PhD student in applied math at the University of Cambridge, and also part of BloodCounts with the other 2. And I'm going to be talking about a little more specifically the results we want to show today. So we've been talking about this blood count test, but what actually is it? So the complete blood count, or the full blood count as it's known in the UK, is the most commonly used medical test. At 3.6 billion per year worldwide, that's 10 million a day. And as such, it's essential for decision-making in any kind of medicine, really. And the way that it's done is that normally, a doctor sees a patient, then they want to get maybe bloods and vitals. If you've ever heard that before, they will do a blood count. And they take a blood sample of the patient, run it through an automatic haematology analyzer machine, and that machine will spit out some numbers, for example here, hemoglobin concentration, white cell numbers, blood platelet count, things like this. Sort of numbers that have been the same for decades and that doctors know how to interpret, and then on a patient-by-patient basis decide on what to do next with the patient, what other tests to run. But we have found actually that internally, to get these numbers, the machine perform single-cell granular measurements on the cells in the sample through multiple different measurement techniques. This here is a flow cytometry example. And we found unique signatures for various different disease conditions within this data. And this is, of course, you can imagine every single dot here is a cell in the sample. Very hard to interpret for humans, but for pattern recognition algorithms that we work with all the time, it's actually very nicely to train. So we've been able to identify some signatures here, as an example, influenza and COVID. But the concrete case that I want to talk to you about today is iron deficiency, which is a highly prevalent condition, especially here in these darker red areas. But it's a bit of a misleading map, because even in the UK and the US, around 1/3 of all young women have iron deficiency, which is quite troubling since it has such large health impacts, from just exacerbating many different conditions to even provable links to productivity and GDP reduction. And the task that we're looking at today is detecting iron deficiency in blood donors with Federated Learning. And blood donors are especially a tough population for this, because they are bled constantly, so iron deficiency is more prevalent in this population, but also they're generally healthy presenting, so it's even harder to detect these kind of conditions there. And as Joe mentioned, since real data between sites and between populations is non-IID, we had to come up with an aggregation algorithm and implement it as a flower strategy called FedMap that is about personalized federated learning while still using the global knowledge through a bi-level map estimate. And so the way it works, just high level, is you train locally, you send the models to an aggregation server, where then we compare the parameter distributions of the model and find an overall distribution that we can then share back to the local sites, where we can then use that information as a global prior that we say, sort of, you can imagine, you can train your own model, but you have background information of what other sites have gathered. And through this, you still have personalized federated learning, but where you still have the global knowledge. And so the task we're looking at here today is real blood donor data that is partitioned into 3 training sites. The first one having a relatively high proportion of non-European ancestry donors. The second one having a lot of retirees. And the third one mostly young and healthy people. And this is really this realistic mix of UK blood donor sites with the non-IID component that we see all the time. And then we also wanted to ask the question, if we have a new site added, where there will be, maybe it's in an area where there was never a blood donor center before, there will be mostly first-time donors when they start donating there. Can we use our already trained model without having to do all this FL stuff again to get good results there? And so I'm going to hand over to Fan to present these results.
Hi everyone, I'm Fan. I'm a PhD student from the Maths Department, University in Cambridge, and I'm also a software engineer on BloodCounts as well. So today I'm going to show you the BloodCounts federated learning dashboard. We're built based on the Flower platform. So I'm going to just click. Oh. The other screen. So can I just show me the other screen? Yeah, so I have this screen.
You want to show this?
Yeah, this screen. Yeah. Okay. Yeah. Brilliant. Cool. Thanks. This platform we designed and developed for like different types of users for blood counts. We have clinicians, we have machine learning scientists, and we have software engineers. So for different users, they have different requirements. So this is a unified place that you can visualize and manage your federated learning tasks. So the first section, connected sites, that'll give you kind of a bird's eye view of what sites are currently connected. So the moment we deployed a flower onto the 4 sites across 2 continents, you can see, and if you hover over on those sites, and then gives you an idea where they are, and also gives you an idea of the sample size and and the primary care samples and the secondary cares. And then the second section gives you kind of insights of site-specific Federated Learning task, how they are going, how they're how they perform. So you can see from the overview. I will be quick. So give you the overview of each site and how they perform, and also like a more granular performance, and also hardware like usage, also that. And then we're going to show you the results for the tasks that Daniel just mentioned. So by clicking here, that brings you to this page, and then you can see the 3 sites, how they perform, and those 4 performance metrics, they're more important for clinicians to see what is kind of a performance for the Fed learning. And also the green brackets shows you the difference between the Fed learning and also individual training. So we use the individual training performance as kind of baseline, because all the sites, they are more care about how much performance I get if I use this Fed learning, or the improvement. And also if you just click on one of them, it shows the specific performance. And then if you scroll down here, and then here is very important, is as Daniel just mentioned, we use the global prior. So when we built the global prior, so we can actually use that global prior to train and validate on a new site. So if you just select the one that's trained, and then that's the new site, and then you click in here, soon as this running is just train and validation on the new site, and also train on the individual training as well. So this give you the performance metrics on the new site. So, and if you look at the numbers, they're all the Fed learning approach, they outperform than the individual training. So then I'm gonna just. Cool. Thanks.